right, let's get this away. So we got a little bit of material to finish up today. I think we should get through all of it. If not, in the first 10 minutes or so of Wednesday's class, we might finish up new material and then kind of transition into doing some exam review. Those two practice exams are up on Canvas. I think they call the folder exam on practice materials. It's got a formula sheet up there that you'll have for the exam as well. I'll put up a ungraded survey on Canvas after class today. It's got 2 questions that would just maybe help me direct how I'll do the review to make it more beneficial for you. So I would appreciate it. 90 points, so I guess it's not a huge incentive, but the incentive would be if you respond to that, it'll make the exam review on Wednesday a lot more beneficial for you. So I'll have that up there. Now, obviously, I need to see the results before Wednesday, so I'll probably set the date to be the end of the day tomorrow. So if you don't mind getting on there this evening or sometime tomorrow, fill that out. Hopefully, we can make Wednesday's class a little bit more efficient. Okay. We left off kind of we've already talked about these discrete random variables. And we said we have a very specific one, which was the binomial. So the setup was you can either see a success or a failure, right? There's 2 outcomes. It's a binary result. And then we had this equation, there we go, that gave us the probability of a certain number of successes. So this was like if I flip a coin 10 times, what's the probability it comes up heads 4 under 10? Right? Or if I select somebody at random, if I select 100 people at random, what's the probability 14 of them have blue eyes? Right? So we had a cap in the number of successes we could see, however many n trials we were running. We then had the underlying probability of success in any one trial. And then X was just this number of successes we were interested in finding the probability of. Okay. So I think we worked through an example. We kind of had this coin flip, right? 10 times. It was a biased coin. So the probability that it comes up heads is 0.4. And I then want to know what's the probability I see exactly 4 of them come up heads this time. And correct me if I'm wrong. We talked about all this, right? We worked this for okay. I'm trying to watch the video again on YouTube right before class to make sure that that's where we're at. So we identified the 3 things that we needed, right? Our number of trials, the number of successes we went through each find the probability of, and this underlying probability of success on any one trial. And then it's a matter of plugging it into this binomial formula. Now, we said a couple things that can make this easier. First of all, do the math we can do in our head before we go to our calculator. I mean, 10 minus 4, hopefully we can that's 6. Or at least we can put it into a calculator and figure out that's 6 or 4. You know, we can put this huge long formula into our calculator. We also said that factorial is one thing that can kind of help us moving forward. And I think I made the point of, I said, put 100 factorial into your calculator, what happens, it freaks out. So if we had an even crazier example, maybe something like 20 factorial, and let's say we'll do 2 factorial. So X would be 2, N would be 20. We've got some other stuff here. We said that this fraction that is pretty nasty that has this factorial business going on, which once again, I would try to find that button on your calculator. It makes your life a little bit easier. But even if you didn't, knowing the definition, we could start to write this out. So 20 times 19 times 18 times 17, all the way down to 1, that's 20 factorial. We then had 2 factorial, which is 2 times 1. And then 20 minus 2 would be 18 factorial. So that would just be starting at 18 and multiplying down to 1. Well, this is where we said, well, look, everything, past 18 would cancel. I can just enter that into my calculator, even if I can't find my factorial button. So I think that's kind of where we left off. Think about a couple other examples and some other wrinkles we could throw into these binomial distribution examples. So I think did we do this one? The basic one with the 5 people having a college degree, if I remember right. We worked through this one, but I didn't get to make a point yet. So we have this example where 30% of adults have a college degree. So if I select any one person at random, the underlying probability of success, or that probably they have a 4-year degree, is 0.3. And then I'm looking at 5 individuals. So I've got 5 trials, and I'm interested in finding the probability that exactly 3 of them have a college degree. So we went ahead and we plugged all those values into our binomial equation, and we can get that probability. Okay. So here's where I think we kind of left off after doing a little bit of review. So let's think about if I put the probability on the y-axis and I think about the different outcomes I could see. So out of 5 people, what's the smallest amount of people that could have a college degree? Yeah, 0 out of 5, and it's discrete. So 1, 2, 3, 4, 5. Right? I don't think that we did this. I might have mentioned it, but I'll kind of be a little more formal. If I want to calculate the mean of any binomial, it's kind of this intuitive result. Now it's easy to do when I have 10 or 100 people. You know, so if I have 100 people and the underlying probability that somebody has blue eyes is 0.15, the most common number of people with blue eyes out of 100 would be 15. Or if I had 10 flips of a coin, what's the most common number of heads I'll see? Well, 0.5 is probably a head any 1 coin flip. So out of 10, the most likely outcome would be to see 5 out of 10. So all I'm really doing there in my head is taking that number of trials. So in those 2 examples, I did 10 times 0.5. That gave you the mean or the expected value, right? Remember these discrete random variables, we don't know the outcome. We're trying to predict the future. The other example, I said 100 people, probably any one person has blue eyes is 0.15. Oops, sorry. So that would be 15 expected people out of 100 on average. So once we find this mean, this is going to be our most likely response. Okay. So here, what's my N? 5 individuals. The underlying probability of success is 0.3. So my mean is 1.5. So don't think I made this point. But if it's discrete, I can't see 1.5 people have a college degree. I can see 1 person have a degree. I can see exactly 2 out of the 5 have a degree. So if I ever end up with a mean that is a decimal, I know that the values on either side of it will be the 2 most likely outcomes. Now, if it ends up just being an integer, like 5, well, I know 5 would then be the most likely outcome. So here, if I'm thinking visually, I don't know off the top of my head, I'd probably have to use that binomial equation to figure it out, but I at least know that 1 and 2 will be my most likely outcomes. Right, those are the 2 values on either side of this mean. Now, as I move further from that mean, so just kind of a reminder, my mean here was 1.5. I'll kind of make this point outside this example, then we'll come back. If I'm flipping a coin, and I think I did this last class, you know, it's pretty likely I get 5 out of 10 come up heads. It's a little bit less likely I see 6 out of 10 come up heads. It's even less likely I see 7 out of 10. Even less likely I see 8 and then 9 and 10. All 10 out of 10 come up heads, right? Which, as I move from that expected value or that mean, in either direction, the probability of a smaller or a higher number of successes starts to decrease. Right? These are my 2 most likely outcomes, and the probability of other outcomes further from that is going to be getting smaller and smaller. I think it's kind of intuitive, right? I think about flipping a coin 100 times. What's the probability it comes up heads 60 out of 100? Probably not that low. It's probably fairly likely, right? I mean, 50 would be the most likely outcome. But then what's the probability I see 80 out of the 100 come up heads? It's got to be pretty rare. What about all 100? I got to imagine the probability there is almost 0, right? If I use that binomial equation, I compute it, I'm going to get something that's out to like some ridiculous decimal point. And I'll show you how we do this in Excel and kind of walk through an example like that. So why am I setting this up this way? We just found the probability of 3 was 0.13. So following along with me at all here, I ask you this next one, right? What's the probability? And this kind of helps me see where you're getting the principles. You're getting too lost in the equations here. Also gives you a little bit of time to work on this, talk to the people around you. All rates and write the general form of the equation. But let's say now instead, I've got the same setup, but I now want the probability that exactly 4 people have a college degree. So I'll give you guys a little bit of time to work on this. Might be, based off what we just did, a little bit easier than kind of having to use that formula over again. So remember, what we just found, the probability that exactly 3 out of 5 had a college degree was 0.13. So what's the probability looking at these 4 values that exactly 4 of these 5 people have a college degree?
So what's N?
right? So we're still asking 5 people, right? It's the same setup we had before. Okay. Probably any one person has a college degree is 30%, so a probability of 0.3.
Mine's not going.
I'm going frequency.
Should be on A, is it not?
I don't think it's on A.
Here, let's go back. I guarantee I probably selected the. Oh, because I was at my office. So never mind. We're not going to use these because I forgot the damn thing in my office today.
So actually, probably on the way out, I might just have you all write your name down, and that way I can kind of just give you full, I'll know that you're here. But this one, you should already have an answer to. You don't have to use that equation, right? I mean, if we hadn't already done the previous work, you would need to use that equation. Your n would be 5. Your x would be 4. And p would be what? 0.3. Now, one thing you'll notice, instead of putting this all in my calculator, let's just do the basic math quickly. I mean, 5 minus 4 is 1, right? So 1 factorial is just 1. I can really ignore that. Multiplying and dividing by 1 doesn't change anything. Here I've got 5 minus 4. So this is just going to be 1. Raising anything to the 1 power is just itself. So I really don't have to worry about that either. So I can kind of simplify this formula before I go try to enter this into my calculator. Now, I don't actually have to do this based on what we previously did. Based on what we previously did, which of these has to be the correct answer? A. All right, why?
Further away from.
It's further away from that expected value, right? I know if the probability of 3 is 0.13, the probability of 4 has to be something even smaller. And then the probability of 5 has to be something even smaller than that. So the only thing that's smaller than 0.13 here is A. Questions on that? Does that make sense?
Sorry about not having that. I was rushing to class early now, but I completely forgot to grab that.
But that's okay. Right. So here's the kind of, we plugged everything in. We should be able to reproduce this answer. So these are good ones, even if we didn't work it out in class. You knew that it had to be smaller than 0.13. It'd be a good thing when you go back to be able to reproduce this answer by entering those values into your calculator. Okay? This is tricky to use this binomial distribution, but entering your calculator, I think it's a little bit tricky. So we want to make sure that you can do that. I think just more practice, right? And some of those connected homework problems have some in there, so you get a little bit of practice with those. That's due when? Anybody know? End of the day Thursday, and then one more day for the Excel assignment, kind of end of the day Friday. Just based off of when I assign those, and that hopefully gives you the weekend to study. Hopefully you have already been working on those, get them done earlier in the week. You have more time to kind of look at those practices. So let's do a little bit more with this. So let's say we have the same setup, but now I want the probability that at least 3 out of the 5 have a college degree, right? So now what I'm really saying is, what's the probability that greater than or equal to 3 people have a college degree? Well, with these binomial distribution setups, I can only ever see one specific number of successes as my outcome, right? Either exactly 3 out of 5 people have a degree, or exactly 4 out of 5 people have a degree. Can't have both of those occurring at the same time, right? And so each one of these different numbers of successes are mutually exclusive. So when I'm wanting to find the probability that's greater than or equal to 3, what I'm really saying is, what's the probability it's equal to 3, or it's equal to 4, or it's equal to 5? And I stop there because my number of trials here is just 5 people. If this was 50 people, I'd have to go probability that 3 people have a degree, plus 4 people have a degree, plus 5, plus 6, plus 7, all the way up to, let's say 50, right, people? That's going to take me a while, right? So this will kind of help us point out 2 things. The first, whenever I want the probability of a range of values, I'm just taking every value in that range, finding the probability of those different number of successes, and adding them all up. Now that sounds simple, but in practice, what do I have to do to find each one of these probabilities? I've got to use that binomial distribution function, right? That's what gives me the probability of different number of successes. Right? So I have to use it 3 times here, which isn't crazy. I probably wouldn't even ask you to do that in the exam though, because that's going to take some time, right? And if we're limited on time, I'm not, trying to make sure that you understand how to do this. Obviously, there will be a time constraint. You should be able to do it somewhat quickly, but I also don't want you to just, if you understand this principle, you could do it for 3 probabilities or you could do it for 40, right? If I gave you enough time, it would just take a much longer period of time. But I might kind of ask you to do this and find 2 probabilities and add them together. So maybe X is greater than or equal to 4. Yeah.
So for your example of it being greater than or equal to 50 or whatever, or you'd have 50 trials or whatever, couldn't you just go backwards and subtract 1?
Yeah, so you're jumping the gun. So I'll get there in just a second, but we've already got this work basically done, just to kind of make the point for this specific problem. What you're saying is you could actually work the other direction as well. Now here, that wouldn't help us out, right? So let's think about this is my event A. What's another way I can find the probability of A? Just 1 minus the probability of its complement. Well, what's the complement of being greater than or equal to 3? X is less than 3. Well, I can find this in the same manner. Just take every outcome that fits this criteria and add those probabilities up. What's the first outcome that meets this criteria? Well, remember, it's discrete, so being less than 3, the very first outcome would be 2. So I could take the probability equal to 2, 1, 0, subtract those from 1, and that should give me the probability of my event as well. Now here, that doesn't save me a lot of time. It is kind of easier to use that binomial function when X is 0. There's a lot of things that cancel, but I'm still having to use that binomial function 3 times. Well, what's a scenario where it could save me a lot of time? Let's say I've got something like a relatively low probability of something occurring, so maybe like 0.01 or something. So then maybe I've got 100 trials. Maybe I'm interested in, okay, what's the probability that I see X be greater than or equal to 2? Well, if I do this, right, I take the probability X is equal to 2, plus the probability X is equal to 3, plus probability, I have to go all the way up to 100. That's ridiculous, right? But if I just think about, this is my event A, well, I could also find this by taking 1 minus the complement. What's the complement of this event? Being less than 2. What are the only outcomes that fit that criteria? X could be equal to 0 or 1. I can do that, right? It's a little bit more manageable, right? So using some of this stuff we've already talked about, like the complement rule, turn something that looks like, oh, this is going to take me forever. Like, I can't even really do this by hand. The factorials start to be like things my calculator can't handle. If I use that complement rule, oh, actually, this is going to take me a lot less time. This is something I can actually solve fairly quickly. Does that, any questions on that? Does that make any sense why we can do that? You can think about it visually. If I want the probability, and I'll use this example just to highlight it, you could do the college example over here. So I don't know, maybe this is like 0, 1, 2, 3, 4, all the way up to 100. Right? So these probabilities probably start to get really, really small. So yeah, I could use that binomial equation, find the probability X is equal to 2, add that to the probability X is equal to 3, all the way up to 100. But I know that if I take the probability of every possible outcome, those should add up to 1. Probability of every possible outcome should add up to 1. So if I'm trying to find the probability X is 2 or greater, well, I could just take the probability X is equal to 0 and 1 and subtract those both from 1. I can go out to this kind of right there. And the reason why that works is because I know that if I take every possible outcome, those probabilities have to add up to 1. Okay? And so hopefully this is kind of a visual that kind of helps with that. So we could actually go through, the only thing left we have to do, we already talked about the probability X is equal to 3 or 4 in this example. The only thing left to find is if all 5 out of 5 have a college degree. Now, once again, just to point out, this should be really easy. I talked about the roulette table example last class, and really it simplifies down if you want to know what's the probability of all of these are successes, right? All 5 have a college degree. Because notice, what's 5 minus 5? 0. 0 factorial, I said, was 1. It was kind of this weird outcome. Kind of like taking anything to the 0 power, it's just 1. So we can ignore that, because 1 times anything or divided by anything, it's the same value. 5 factorial over 5 factorial is 1. This whole fraction is 1. Well, then have an actual value I have to compute here, 0.3 to the 5th. But then this component, if I'm raising it to the 5 minus 5, I'm raising it to the 0 power, well, this is just 1 as well. So when I want to find the probability that all of them are successes, everything simplifies except for what's in the middle there. Take the underlying probability of success and raise it to whatever that number of trials is. Now that only works if we're looking for that probability that all of our trials are successes. Right? But yeah, when we do have that, it kind of simplifies pretty nice. Any questions? So if you think about that roulette table example, I want to know the probability that all 26 spins came up black. It would be my underlying probability of success. That number of trials. If 0.3 to the 5th is 0.002, this is like, you know, a ridiculously small number. So you can kind of calculate these things relatively. Any questions here before we kind of move on? I kind of already alluded to this, but the mean, right, we're going to talk about this, the mean of our binomial distribution examples, just take the number of trials and multiply by the probability of success. Right? Now the variance, so that's fairly intuitive. The variance is not intuitive, but if you treat this like any other discrete random variable, what would you do? Well, you'd start with the very first x value. You would subtract the mean. Well, the mean is just n times p. Square that. Multiply that by the probability x takes on this specific x value. Well, this is the binomial distribution function. You would then add to that the next x value minus the mean, so on and so forth. Believe it or not, Google the proof. You can come talk to me about it. It's boring and takes a lot of time to simplify it down. But if you write this out, and it doesn't matter what your number of trials is, it always simplifies down to, you would just take n times p, or the mean, times 1 minus p to get the variance. Like I said, the proof's not that interesting. For the sake of what we're going to do, we just need to know that that's the formula that we calculate the variance for a binomial distribution. We don't have to go through all these steps. That simple formula will give us a variance. Which means if I want the standard deviation, all I have to do is take the square root. Yep. Just like we have in the past. Okay. Well, when finding the variance of these, if I ask you on the exam to find the mean and the variance of a binomial distributed variable, and I give you the number of trials, product success, that should be easy. All right. Because you'll have these formulas in front of you. I think Wednesday after we do some review, I'll kind of break down the formula sheet, showing you like formula sheets groups the equations kind of in chronological order. So it's a little bit easier to kind of identify where are the relevant equations for this type of problem. So a nice visual, kind of thinking about this idea of the mean being the most likely outcome. I'm going to kind of walk through that. I don't often steal things from the book, but I stole this. I really like this, this set of pictures that they have in there. So this will start out with n equal to 5, the number of trials will be 5, relatively low probability of success. So there, my mean would be what? Probability of success is 0.5, number of trials is, sorry, 0.1 is my underlying probability of success. Number of trials was 5. So n times p, 5 times 0.1 is 0.5. So the two most likely outcomes will be 0 and 1, right? The two integer values on either side of that mean. Sure enough, if we actually compute these probabilities using that binomial probability mass function formula, 0 and 1 are the most likely outcomes. Now, when we have a situation like this where the mean is 0.5, we're not saying 0 and 1 are going to have the same likelihood of occurring. We're just saying they're the two most likely. So notice here, 0 is a little bit more likely than 1. And then as we move further from that mean, the probabilities decline. Think about it this way, like if on average out of 5 trials, I see that 0.1 are a success, it's going to be pretty unlikely I see all 5 out of them, all 5 out of 5 be successes. If I then move, so what kind of think about here, what type of skew would I have in my distribution? I have this right skew. Now, as I move the probability of success up, so it goes from 0.1 to 0.5, I kept the number of trials the same here. Well, 0.5 as my new probability, my new mean would be 5 times 0.5 or 2.5. So 2 and 3 should be the most likely outcomes now. Sure enough, visually you can see they are. And then as I move in either direction, the probability of a higher or lower number of successes declines. Here we've got a nice symmetric distribution, right? If I could like split this in the middle, it would pull on top of itself. No skew. And then if I look at a higher probability of success, keeping the number of trials the same, well now my new mean 5 times 0.9 is 5 times 0.9 is 4.5, making 4 and 5 the most likely outcomes. And as I move further from that, the mean, the probabilities decline for those number of successes. So I think this is a nice visual to kind of show as we change that probability of success, what's that going to do visually to our entire distribution? And that makes sense. Like if 90% of people have a college degree, then when I ask, randomly select 5 people, it's going to be pretty likely 4 or 5 of them have a college degree. Or I want to think about out of 10, 9 or 10 would be pretty likely outcome. If 90% of people have a college degree, it'd be very unlikely that I see 0 out of 10 or 0 out of 5. And then as I increase kind of my number of trials here, you can see it basically just makes my distribution more granular, right? I get that the probability is kind of spread out over more outcomes. So notice here, when I've only got 5 outcomes, the probabilities can be as high as like 0.6. Oh, if I've got just a wider range of possible outcomes now, 0 to 20 instead of 0 to 5, those probability values are spread out over more values. And notice we kind of get even the most likely outcomes now have probabilities of only 0.2. And then if we go to even higher number of trials, now those most likely outcomes still only have probabilities of about 0.9. Any questions on that? This, I don't know, these are a way to kind of think about this differently, maybe help solidify kind of what the binomials is looking. So this should be a relatively easy one. Like going back to that mean and variance. Once again, we're really trying to hammer this because it's pretty easy. The mean should just be the number of trials times the probability of success. We've already kind of discussed for our example earlier. We had 5 individuals, probability of success is 0.3. That should be 1.5 of our mean. From there, our variance, we have that equation with just n times p times 1 minus p. So 5 times 0.3 times what? 0.7, 1 minus 0.3 should give us that variance of 1.05, if I remember right. Yeah. So that shouldn't be too bad. It's just an easy point. The only wrinkle I might do there is ask for the standard deviation, in which case we would just take the square root of 1.05. Okay. Questions? I think I'm going to skip this and see if we have time at the end. This also might be something that we can hold off on the use at the very beginning of kind of review. I want to try to get through the Poisson stuff today, and we might kind of come back and retouch on the binomial. But just thinking about different situations we can use. This has to be where we have a success or a failure, underlying probability of success, and we have to have it cap a certain number of trials. Okay. So I might come back to this one just to kind of revisit the binomial when we're doing that review on Wednesday. So I want to show you how we do this in Excel. This should help you with the last little part of that Excel assignment. The bulk of that assignment was stuff that we did back when we were looking at building those frequency tables and then turning them into joint probability tables. But there's a couple questions related to the binomial, right? So I'm just going to open up, and these will kind of accompany it. Believe it or not, I looked this up, and it's primarily older people, but there's actually a pretty high percentage, especially if you look at, I forget what state this was, of the population. So that's millionaires. If you just look at their kind of asset value, the retirement fund. So I had what, 6.7%. So let's go. I'm just going to open up Excel, blank document. You're going to change the view so we can, oh, maybe we can change the view so I can see what I'm doing here. And I'll show you how to use the built-in function. So that probability mass function is built into Excel. So, all right, it's actually a little bit easier to work with. Now, it's got some pitfalls, and we need to be a little bit aware of them. But it does make life quite a bit easier. Okay. So the setup's going to be, we're actually here, right? We're looking at a certain number of trials. I think here I had 100 different people were surveyed.
So I'm just going to enter these numbers into cells here. The underlying probability that any one person was a millionaire from this group, like I said, I think this was a state in the Northeast, was 0.067. Okay. I then might be interested, okay, what's the probability that X, this random variable for the number of millionaires out of 100 people that I'm surveying, is equal to 8? Okay. So I go up here, my X value in this specific example would be 8. Okay. Now I know that if I could do this by hand, I've got the 3 things I need. I could plug them into that binomial equation. Just going to take me some time to enter this in my calculator. Well, in Excel, there's this built-in function, binom.dist. Okay. Now it kind of reminds me what it needs, but it basically needs 4 things. So if I've got this binom.dist function, Excel wants me to tell it 4 things. The first is going to be our number of successes. This would be our X, all right? The next thing is the number of trials. The next thing is the underlying probability of success. And then the last thing is whether or not we want to make it cumulative, all right? So remember, this idea of cumulative means start at this value and go all the way back down to the beginning of time. Well, we don't have a time example here. It's go all the way back down to 0 successes, okay? So for this one, we don't want it to be cumulative. So the way that we turn this on and off, and I think sometimes it'll tell you you can type in the words true or false. Maybe I'm just a numbers guy, and so it makes more sense to me, but you can just use 1, 0, 2. 1 being true, it should be cumulative. 0 being no, it shouldn't be cumulative. But I guess you can use the words true and false as well, and Excel will pick that up. So I'll show you both ways. So here, the number of successes we want to find the probability of is 8, comma, the number of trials, n, reminds us, is 100. The underlying probability of success we had up here at 0.067. And then I wanted the probability of exactly 8 out of these 100 people being kind of considered millionaires. So I plug in that 0. It does not make it cumulative, finds just the value of that 1x, sorry, just the probability of that 1x value, okay? So if I hit enter here, it tells me that there's about a 12% chance, right? Or probability of 0.12. Yeah.
You know whether it's true or false again.
So up to this point, so anytime we're looking for the probability of just one specific value, that's not cumulative, right? We just want this value. Anytime we want to know the probability it's less than or equal to a certain value, then we make it cumulative. So I'll show you a couple examples of that here in a second. And like I said, if you don't want to put a 0, 1 in there, you can think about it as, well, no, I don't want it to be cumulative, so I can put in the word false. And notice it works the same way. I always just use 1 zeros because I just think it's a little bit easier. Okay. All right. Let's say, and I'm gonna be lazy with the, instead of trying to find the less than or equal to sign, just type it in the way that we would kind of say it. So let's say I want the probability X is less than or equal to 8. Okay. So now I do want it to be cumulative. Really, what I want Excel to do is find the probability it's equal to 8 number of successes, then add to that the probability that I see 7 successes, add to that the probability I see 6, all the way down to 0. What's nice is I can use that binom.dist function again. Whatever X value I tell it, that's the value it's going to start at, and then go add up the probabilities down to 0. So here I want to start it at 8. I'm keeping that number the same to make it easy. I'll show you a different example in a second. Then I've got the number of trials up here. The underlying probability of success is right here. And now I do want it to be cumulative. So either put a 1 or put this word true. And it basically does all that work behind the scenes, uses that binomial distribution function 9 times, including 0, right? And adds them all up for me. All right, this can save me a lot of time. Okay. Any questions on that? Yeah.
The 0 you said is like an exact value.
And then if I put a 1 or the word true, that's going to start with whatever X value I tell it and add up the probabilities down to 0, right? Essentially, visually, it's going to start with whatever value I tell it, find all the probabilities down to 0, and add them all up. It just does it all behind the scenes. I can't see. So the reason why I have to be careful using the cumulative kind of component of this is, let's say, well, before I go to that, I'll show you one other thing you can do that kind of has some good applications, and then we'll kind of come back. I think this might help. So let's think about different X values, and I want to find the probability of seeing them, all right? So let's start at 0. Oh, that's not 0, that's a O. 0, 1, 2. Now I could kind of type this in all the way down to 100. So a nice little shortcut in Excel that we haven't really needed to use yet. If I go over here to that right corner and I right click, let's see if I can do this on my laptop, and I scroll down and I let go, I'll have all these options. Now I could just copy the cells. If I would have left clicked and dropped it, it automatically copies. If I right click and drag it down, it gives me these other options. If I go to fill series, it defaults to increasing it by 1, right? There's actually, I could do it again, and there's actually ways you can change it to jump by 10 or jump by 2.5 or whatever kind of you want. The default is always 1, and that's probably the most practical use, right? You want to kind of get all these different X values, and then you want to calculate something next to them. Because think about now I can use this binom.dist function, the number of successes I have right here, comma, the number of trials, and I can click with my mouse on cells, or I can use my arrow keys to navigate up to whatever cell I want. So I'm just going to do that because I hate using my mouse pad. I don't have my my batteries actually died earlier today in my mouse. So the next thing I want to tell is the probability of success. And then I don't want it to be cumulative, so I'm going to put a 0 there. Now, if I copy this down, all my cell references will change, right? Which I do want to keep updating that number of successes, right? I want the next row to find the probability that I see 1 success, and then the probability that I see 2 successes. What I don't want to change is the number of trials or the underlying probability of success in any one trial. So we said we could do what to those? Yeah, absolute. Actually, I don't think I used that term, so you must have heard that somewhere else. But yeah, absolute reference. You can freeze these cell references, or you kind of put dollar signs in front of them, right? So usually this is the F4 key, or on a Mac, we said it was Command T, and it automatically throws those in there for you. Yep. So now when I copy this down, the only thing that changes is the number of successes that I'm finding the probability of. Another nice little shortcut here. If I double left click, when I go to the bottom right corner and I double left click, instead of copying this down, when I double left click, it automatically copies that down for me and updates those cell references. So instead of, dragging this down so that it copies it, it'll actually go all the way down to the very last value. Notice by the time I get to 28, right, this probability is what? 4.6 e to the negative 11. So this scientific notation in Excel means move that decimal 11 places to the left. This is 0.1004. This is 0, right? This is a very small probability. And it makes sense. If 6.7% on average, right, was kind of what we see, the percent of millionaires. If I have 100 people, the most likely outcomes would be, well, the mean would be 100 times 0.067, or 6.7 people. So 6 or 7 will be the most likely outcomes. By the time I get to 28, that's so far from that mean, that probability should be pretty low. And I can kind of prove this to myself if I go back up here, right? The 2 most likely outcomes, 6 and 7, have the highest probabilities of occurring. And then as I move in either direction, those probabilities start to approach 0. Right? So, I could graph these if I really wanted to. I don't know. I'm not going to necessarily waste time on it today. It's not that interesting for what we're about to do. But this is a nice way to set up kind of using that binomial function a lot of different, for a lot of different X values very quickly. And you might imagine, like, this is really like, if I'm working, well, so especially for like a lot of you finance majors, like, probably not supposed to this, but you probably have some type of a sales job when you kind of enter into the world, like to get your feet in the door. A lot of times you'll be doing some of that, or a lot of you will go into working like an insurance company, or you'll be working for some company that's trying to predict like how many loans are going to default, right? Or how many of our clients are going to leave us? How many new hires do we have to make next quarter? Like, you're looking for these number of successes, right? Whatever you're interested in finding the probability of, you look at historic data to get an idea about the underlying probability of success in any one trial, and then you build these tables, right? Because, you know, let's say I'm interested in loan defaults. If my company can't handle more than 10 loans being in default, and I find the probability that 10 or more loan defaults here is like 0.34, that's a pretty high probability. I might be really concerned next quarter that I'm going to have too many loans default, and then I'm going to be in a bad situation, right? I'm not going to have enough money coming in, you know, to cover whatever my expenses are as that insurance company. So this is pretty applicable to build these tables. This is another thing you'll see, like actuarial science. You would have tables like this where you're trying to predict the number of success and you have all these associated probabilities. Now, the reason why I did this is to show you some things in Excel, but also I can prove to myself that this binomial distribution function is working correctly when I make it cumulative, because if I use that sum function, well, if I want the probability x is equal to 8 or less, I could just take the probability x is equal to 8, sum up or add up all the way down to the probability x is equal to 0, and that should give me the exact same probability. Okay. What if I wanted the probability that x is greater than 8? So I guarantee you, people will do this wrong in the Excel. I shouldn't say I guarantee. More likely than not, I usually see people do this wrong because they weren't listening to me in class. So that cumulative option only allows me to take the probability of a certain number of outcomes or less. If I want the probability being greater, I can't put like a 2 in there. Or I can't put another number in there to tell it, take this number of successes and start adding up. All right. So how could I find the probability x is greater than 8? If I know the probability x is less than or equal to 8, I just use that complement rule. So in practice, I don't have to break this down into 2 cells. So I could here just do 1 minus that. Now, what I could also do if I wanted to put this all into 1 cell and I didn't have this previous work, whoops, I can use built-in functions and math within the same cell. So I can say, look, use this binomial distribution function, find the probability that it's 8 out of 100 with this underlying probability of success, comma, or less, right? Make it cumulative. So that's my event A, finding the probability x is less than or equal to 8. Well, if I want to find that, it's the same as 1 minus its complement. I want the probability x is greater than 8. Its complement was being less than or equal to 8. So I can just do 1 minus that. And it should give me, oops, I hit shift. I hit, there we go. It give me the probability, right? So there's no option, I don't know why. It would be very easy for them to program in, like, to make the option. If I put a 2 in there at the end to just find me the probability being above that value. I don't know, they didn't feel the need to write that into that built-in equation, right? I guess we're lucky enough that they programmed that into Excel, right? We can use that binomial equation. So if you do a little bit more work, we want to find the probability of being above a certain value. Okay. Any questions on that before we keep moving? Okay, let's see in a cell again, or just one other thing I'll tell you before we go back to talk about the Poisson, to just be aware of a pitfall of using this. Let's say I wanted the probability of being, I don't know, less than 3. I type this in. I say the number of successes I want is 3 here. Number of trials I want is 100. Probability of success here, make it cumulative. Why is this not going to be the correct answer here? So when we make it cumulative, this binom.dis function starts with the x value we tell it. So this is actually going to return to me the probability that x is 3 or less. So if I don't include the equality there, what's really the first outcome that fits this criteria? Yeah, it's discrete. So the very first one would be 2. So what I would actually need to do is put in whatever the first value that fits my criteria is. If I don't include the equality sign, it's going to be the next lowest integer. All right. So here, that I can kind of confirm this to myself by if I take, I want the probability that x is less than 3. Oh, I didn't mean to capitalize that. Well, that would just be the probability of 2, 1, or 0. So if I add those up, hopefully, sure enough, I get what I did. So be careful with that equality. Any questions on this? We're kind of jump back into one final distribution. So I'll let me save this actually right now. And I'll put this up just so you have it under the in-class data folder on Canvas. I'm going to just so you have the exact thing that we worked on. Save it here, binomial, section 5. All right, so I'll post that after class. So we'll go back and we're now going to talk about one final distribution, which is the Poisson. So the binomial was a very specific type of problem where we had a number of trials, so we knew what the maximum number of successes we could see. With the Poisson, we're still looking for the same thing. We still want to find the probability of different number of successes. It's just now we don't have a number of trials. We've got some time interval. So I might show you an example today. If not, maybe we'll start class on Wednesday with finishing it up, where we look at another type of space. So it doesn't have to just be a time interval, but for the sake of the exam, I would only ask you about time intervals. Okay? So you could do this over, like, instead of a certain number of successes over an hour, you could do a certain number of successes over a mile, right? Like, what's the probability I see 50 pieces of trash if I walk a mile of highway, right? It doesn't have to be an interval of time, it could be an interval of space. But we'll kind of stick to time intervals to make it easier. They're also like, for what most of you are going to do, like, whatever be using this for, it's going to be a time interval, you know. If it was like a physics or something like that, like we might go more towards like a space. You know, don't worry too much about these. I'm not going to give you an example that this is violated, but we need to make sure that we have intervals of the same length. So if we're talking about seeing a certain number of successes over a week, all of our intervals need to be a week. If we're talking about seeing a certain number of successes over an hour, all the intervals that we're talking about should be an hour. And they shouldn't be overlapping, right? So every hour should be kind of independent from each other. Kind of like we had independent trials for the binomial. But I'll never give you an example where this is like violent. So we don't have to worry about that too much. So just like with the binomial, what we're really thinking about is we have all these different values for X, and we want to find the probability that we see these different values for X, or these different number of successes over a given time. So the probability mass function looks a little bit different, a lot easier than binomial. Right? So we really only have two things here. The first, kind of similar to the binomial, is just the number of successes we want to find the probability of. We're a little bit more familiar with factorials now. I hope we can raise things to certain powers. The other thing we might not recognize is lambda, right? This Greek letter lambda looks like an upside down Y. And that's just something that's going to be given to us. That's the average rate we typically see over whatever interval we're interested in. So setup for this could be something like up on the gallery, on average, I see 3 accidents every day. And my time interval is a day. The number of accidents on average we see, we look at historical data, is 3. I then want to predict how many accidents do I see tomorrow? Well, what's the probability I see 5 accidents on the gallery tomorrow? My X will be 5. From historical data, the average rate is 3. I've got everything plugged in I need to get this entered in my calculator. The only thing left we might not know is this natural number E. It's kind of like pi. It goes out. I don't think it's, I should have looked this up. I don't think it's an infinite number of decimals like pi, but it's a ridiculously low. I think it might have, maybe it's just theoretical that it ends, but it's crazy. Right? It goes out to whatever decimal really we want or physically be able to go out to. You can't find this button on your calculator. Usually it's like you hit second and it's above one of the other numbers. If not, you can use kind of this approximate version out to the 5th decimal, 2.71828. I forget exactly. You can memorize this out to like 50 spaces with Abraham Lincoln facts. So for whatever reason, it's like Abraham Lincoln was 27 when he got into politics or something, and 1828 was the year he did something. I can't remember what it is, but there's some way you can remember it that way. So I would just say Abraham Lincoln was 27 and he did something in 1828. That'll allow you to memorize it up to the 5th decimal. Okay?
But it should be a button you can find in your calculator. Like I said, it's usually second when you type one number. So really, it's just, we're using this the same way we did the binomial. It's just, I think this is a little bit easier of an equation. We don't have as many factorials. We don't have as many moving parts. It should be a little bit easier. So the kind of setup we have is this guy who wrote this thing called the book of, or the, sorry, came up with the law of small numbers, kind of in response to the law of large numbers. Really famous. I'm not even trying to pronounce his name. So the kind of setup that he has with this Poisson, noticing that when we're looking over a given interval, we typically see things follow the same distribution. This is what we call the Poisson distribution. So he noticed that every year, when we look at historical data, that 0.61 soldiers on average were getting kicked by a horse and dying in the cavalry. So, this is over, maybe the last 50 years, they're looking at this cavalry data and seeing about 0.61 people on average die over a year. So maybe they're worried about losing soldiers and they want to know, okay, what's the probability? Let's see if I remember the number right. There we go. Exactly 3 people are killed this following. Now, what should be the 2 most likely outcomes? So this one, I'm going to jump the gun a little bit, but the mean for the Poisson distribution, well, if we know the average rate over the time interval, then the average of the expected value is just going to be that average rate. So we're literally directly given the mean. So if the mean is 0.61, this follows the same principles as the binomial, that the mean is the most likely outcome. It's the expected value, the outcome that'll happen the most. Well, still discrete. So if the average is 0.61 and the mean is 0.61, what are the 2 most likely outcomes? 0 and 1. 0 and 1. And then as we move further from that point, the probability will start to fall. So my guess is if we look at the probability 3, it's going to be relatively small. I would expect, I don't know, maybe 0.1 or less. Right? It's not too far away from 0 and 1, but it's not 0 or 1, right? So what is the actual probability? Well, we got all we need. We just need the average rate that has to be given to us in the problem. And we know the number of successes we want to here. Successes, something we can kill, but what we're trying to find, right? We see 3 occurrences of this event, with 3 successes. So from there, it's as simple as take that general form of that Poisson distribution. You'll have that on your formula sheet. Plug in your lambda, the average rate. Don't forget, there's a negative sign in front of this, so it's to the negative 0.61. And then you'll plug in your x value. Now it's just a matter of getting this entered into our calculator. Like I said, especially maybe before Wednesday, it might be a really good idea to try to find that factorial part on your calculator. And if you can't find it by Wednesday, ask me after class and I can show you where it's at. Okay? Any questions on this process? It's really not much different than binomial. It's just that we're using an easier function to find that probability. So it's relatively low. Got another example. If I write down the general form here, so if I've got, this is usually the way for the Poisson distribution example, it's lambda to the x, e to the negative lambda over x factorial. So let's say I'm in a hospital, and I look at my data, and I'm like, on average, it's about 1.25 births every hour. I'm trying to make staffing decisions, and I'm worried about, well, man, if I get 3 births in this next hour, I don't have enough staff to cover that. So maybe I'm interested in finding the probability that exactly 3 births happen this next hour. I know my average rate is 1.25. It's a matter of getting this under my calculator to figure out what that probability is. So you're always going to start out with this general form of the probability math function. You'll have your average rate that will have to be given to you. And then your x value is what you're interested in finding the probability of. In this case, exactly 3 births in this next hour. Okay. Questions on this? So try to just get some of these principles, and I might do something that's like this in the exam. Let's say that was one of the possible answers up there. Why could I rule that out right away? So what's my mean here? 1.25. So what are the most likely outcomes? 1 and 2. if the probability of 3 was 0.54, at most, what could the probability of 2 be? It should be one of my most likely outcomes. But remember, these probabilities of every possible outcome have to add up to 1. So even if 2 was the only other option, at most, it would have to be 0.46, making it not the most likely outcome, right? So 0.54 being the probability of 3, I can rule that out right away. I know that if it's not one of the most likely outcomes, then the probability of the number of successes I'm looking for would have to be less than 0.5. In fact, with a little bit more math, we could probably even limit it even more, but at the very worst, right? No matter what your lambda is, if it's not one of the most likely outcomes, one of the values on either side of the mean, you know the probability has to be less than 0.5. Otherwise, that would make it the most likely outcome. Understand what I'm getting at? With that, any questions over the idea? Kind of explain it a different way. Now, from there, I can't really guess between these 4 options. It's a matter of getting this entered into my calculator. We've got it written out. Now it's just a matter of getting this entered in. So you get about 0.09. So I think probably a good thing having these slides, we go back and trying to be able to make sure you can get this entered into your calculator. And, I can give a lot of class time. I mean, it's partially on Wednesday. I think part of what we'll do is I'll let you work a little bit on some and then I'll kind of work through it. So you'll have a little bit of more time to practice that there. You should be able to enter these, once you can see what the setup is, you should be able to get this entered into your calculator and reproduce these answers. And that might just be kind of taking some time to practice along the way, practice as you're studying for this exam, getting these entered into your calculator. Even if you understand it. Even if you understand plugging the values in the formula, make sure you can get that entered into your calculator. So here we'll highlight something else. So what if I want the probability of seeing 2 or more births? So there I'm saying, what's the probability X is greater than or equal to 2? So with a Poisson distribution, right, this really highlights the importance of understanding an old rule. Because if I want to find this, it's just like the binomial. This is the same as the probability X is equal to 2, plus the probability X is equal to 3, plus the probability X is equal to 4. But where do I stop? I don't know. Right? I mean, I don't have a number of trials to cap my number of successes with. So if I want the probability of being above a certain value, it becomes pretty tough for me to solve it in this manner. But what could I do? If I think about this as event A, it would be the same as what? 1 minus the complement. That's a C. Complement. Well, what's the complement of being greater than or equal to 2? Yeah, that X is just less than 2. What are the only outcomes that fit this criteria? X could be equal to, the very first one, that X is equal to 1. Add to that, the probability X is equal to 0. Once we have added those together, subtract them from 1, we should have this like open-ended probability that we thought we couldn't solve. Any questions on that idea before we kind of get into the. So with the Poisson distribution, before the binomial, it was just a pain in the ass to have to like go, use the equation 100 times. With the Poisson, I can't do it. Right? It's open-ended. I don't know where to stop. Right? So I have to use that complement. Now, I could actually from these kind of figure out and like limit what my options are going to be, or at least come up with a ballpark of where this probability should lie. So I try to describe these in this way, and as we do the review on Wednesday, I'll try to kind of give you examples where knowing the principles allows you to limit from these 4 options, sometimes down to even just 1, usually like rule out 1 or 2 of them. So that really, even if you don't know where to start, or you keep entering your calculator and take the right answer, at least you can have a more educated guess. You just even understand the principles of what that you're trying to find. So here, if I'm thinking about, I could see 0 births, 1 birth, 2, 3, 4, all the way up to who knows how many,
right? And I'll just keep going. So if 1.25 is my mean, we said 1 and 2 would be the most likely outcomes. And then, 0 is a little less likely, 3 is a little less likely, 4, 5, 6, 7. So if I'm thinking about the probability that x is greater than or equal to 2, I'm thinking about taking one of the most likely outcomes and then adding up everything, every probability to the right of it. The only thing that doesn't include is 0 and 1. So I'm thinking this probability should be relatively large, right? Like I can't say exactly how large, but if it's one of the most likely outcomes, and then every single other outcome to the right of it, I'm only excluding 2 other possible outcomes. The thing is, it's probably like above 0.5. It'd be pretty safe to say if I'm adding up all of these probabilities and one of them includes one of the most likely outcomes, as well as some values that are pretty close to it, the thing is, it's probably going to be a relatively large probability. And so if I'm looking here, C makes no sense, right? I mean, it doesn't make any sense. That's way too small. D even seems a little too small. So if I'm just making an educated guess, I'm probably going to guess either A or B. Now from there, just looking at, I can't say exactly without working the numbers out, but just visually thinking about this should be a relatively large probability. It includes one of the most likely outcomes and the vast majority of all the other outcomes. Okay? So sure enough, if I kind of compute this, using that Poisson distribution once where x is 0, using it again where x is equal to 1. All right, so plug in 0 here. Notice when I want the probability no success with a Poisson, 0 factorial is 1. I can ignore that. Anything to the 0 power is 1. I'm really just left with having to enter this in my calculator. Then I plug in x is equal to 1. Okay, well, there I have a little bit more work to do. Anything to the 1 power is just itself. So 1.25. 1 factorial is 1, so I can ignore that. Really, these aren't too bad, right? If I kind of eliminate those. So I then take those 2 probabilities, add them up, subtract 1. Okay, I was a little bit off, right? I thought that maybe I could rule out 0.35, but it ended up being I said it was a relatively large probability. So here it probably was a little bit unwise to rule out something as large as 0.35, but I know something as small as 0.038 could have been something I can rule out. So when you're making these, trying to rule out what these possible answers are, be a little bit, what word am I looking for? Conservative, right? Like I really think about, okay, I know this is going to be a relatively large, but relatively large, right? It's just not going to be close to 0, right? So really the only thing we probably should have been ruling out here before we actually plug the numbers in is D. But if you add these up, subtract them from 1, you get about 0.355. Okay. Any questions over any of the process here? Or just questions in general about this?
Well, what if it's like less than or equal to a number?
Yeah, so let's say we had. Let's say we want to hear the probability x is. I wouldn't give you one like this because I'm only ever going to expect you maybe to use that.
It's on the homework bill of like x is less than or equal to 1.
Yeah, so that's not a large number, right?
Okay.
So here I would do something like, what's the probability x is less than or equal to 1, right? What are the only outcomes that fit this criteria? The first one would be x could be equal to 1. And then the only other outcome, remember, we're dealing with discrete random variables, so we can only see integer values. The only other value we could then see is that x is 0. Now we've got 2 probabilities that we need to find. So it would be kind of plugging in x equal to 1 into that. Let me see. So lambda x e to the negative lambda over x factorial. So we would, whatever the problem is, they would have to give you an average rate, or they would give you this lambda. You would plug x is equal to 1 into here, find that probability, then add to that whatever the lambda they give you to the x is 0, right? Plugging in 0 for x, e to the negative lambda, and then x here once again, making your x 0, and add those 2 probabilities. You wouldn't have to subtract it from 1, right? So it's really the same process. It's just that if you want less than, you don't have to do this 1 minus because you're not trying to find the complement. Now, and what I started out saying, so yeah, I would ask you something like this. I'm not gonna be mean and ask you something like this, right? Because then you'd have to find the probability it's equal to 5, plus the probability it's equal to 4, plus 3. We're gonna have a limited time on the exam. I'm not, if you understand how to find 2 of them, I know you could find 5, it would just take you longer, right? So I'm gonna, limit it to if I do something like this, or I might make you use the complement rule, but you're never gonna have to use that Poisson distribution, that binomial more than twice. I don't even know if I can use it twice, might just be once. So I don't know. All right, so. I don't know, this isn't that interesting, it probably doesn't really help a whole lot at this point, but you can do a similar thing with the Poisson distribution. As you move that lambda or that average rate up, well, notice that means that my mean is increasing, so values that are further, my mean's gonna be a higher value, it's just gonna be shifting the distribution so that it's less and less right skewed. The one thing that's interesting about the Poisson, it's always gonna be right skewed. And when we think about why, it never stops. There's always going to be an infinite right tail, right? So the Poisson is really, you can get close to symmetric, but it's technically always going to have a slight right skew to it. This one's not as interesting as the binomial, but it does going to give a nice visual that as you increase, from 0.1 to 0.5 to 5, increase that average rate, higher number of successes, those probabilities start to increase. And then lower number of successes, those probabilities start to decrease. Right? The probability of 0 kind of decreasing as you move from left to right. Yeah. Another really interesting property about Poisson, I can guarantee it. I won't ask you this question on the exam. Well, maybe I'll be really nice and maybe you'll be able to get some bonus points, but the Poisson distribution has a really nice property, which is that the mean, which is just this average rate given to you, is exactly the same as the variance. The same kind of idea. There's a proof out there. You can set this up to, x minus the mean of lambda, square it, times the probability of success, which will be that probability mass function, simplify everything, and it always simplifies down to just be lambda. So, and then the standard deviation is the square root. So that shouldn't be anything too crazy there. Nice property that the Poisson has. So yeah, put the variance the same. So let me think. What do we want to do here for the last 10 minutes? So I'm not going to confuse you with this. So we're going to skip over. So it's not going to make you use it on the exam. If we had additional time, it was something that might be an interesting example to go over. But basically, if we have a setup where we have a binomial and we've got a huge number of trials, like 10,000 here, right? Okay, some things could simplify and maybe I could calculate this, but there could be a scenario where like my n is 10,000. I want to find the probability of 20 successes. So instead of 3, I have 20 in here. And I still don't have a calculator that can handle that large of numbers. Even though I can cancel stuff, it's still a huge number. What I can actually do is convert binomial examples that have really large number of trials, but really small probability of success. So really small probability of success, relatively large number of trials. I can take that mean of the binomial and turn this into a Poisson distribution, right? And the Poisson won't, right? So I think I said here, it's some fancy math. It won't be exactly equal, but it'll be a really close approximation. So if I did use the binomial here, where I had the number of trials be 10,000 and the probability of success be 0.0005, I can get that probability, right? It's just tougher, it's more difficult. There's some situations where I wouldn't be able to do it in my calculator. But if I take the mean of that binomial, which is just n times p, so what? 10,000 times 0.0005, I believe would be just 5. And I use that mean as my mean for the Poisson, that lambda. Well, I can actually find the probability of 3 successes using the Poisson distribution, and it should be a close approximation. So I'll find that mean of my binomial, plug that into my Poisson equation as the mean of the Poisson or lambda. I then have the number of successes I want to find. I think I had some like radioactive decay examples, so 3 of them decay. Plug in my x equal to 3.
and out to the 5th decimal, I'll get the same value. Now, if I were to like find this out to like the 20th decimal, it's gonna be a little bit off, right? When you have a really high number of trials and a really low probability of success, you can actually use this Poisson distribution to approximate it. And like I said, kind of start using the Poisson. I think that's an easier equation to use than the binomial. Now, I'm not going to give you an example where you would have to do that on the homework or on the exam. It's just an interesting thing that in practice, if you continue to take courses above this, I don't know, some advanced stats, or I don't know, even if you're working out there in the real world, you might come across a situation where it makes your life a hell of a lot easier if you kind of convert that binomial into a Poisson. And like I said, I'll use these scenarios to kind of make the point when we start review the difference between Poisson and binomial. I think that'll be a good way to set up kind of the review just over those on Wednesday. The only other thing that I might expect you to do, I'll save this example. I told you I'm not going to give you a time interval example. Or sorry, I told you I'm not going to give you anything other than a time interval example on the exam. So I'll hold up on this example. It was kind of a fun, interesting one. Maybe if we have time, just to give you another binomial example. So let's say that this is not in the slide. This is my biggest one right there. So let's say that over the year, on average, and so that's why I'm writing like the average for the year. The average number of people that get struck by lightning is 48. Okay? I then ask you for the probability that you see 3 people struck by lightning this month. Well, don't have the same time interval. Now, it's a little bit of a stretch on this lightning example, but if I then told you assume that the number of lightning strikes is equally distributed across every month. Right? Like I said, I'm sure there's like a weather person that would say that's not the case, but just for the sake of this example, let's assume that lightning strikes are the same across every month. How could I find this probability? What? No, yeah.
Just convert the year to month.
Yeah, what I want to do, if I had the average rate over a month, well, I've got the number of successes over a month, I'd have my average rate. That's all I need for my Poisson distribution, right? Lambda to the x, e to the negative lambda over x factorial. I would have my new lambda. I have x, 3 people getting struck by lightning this next month. So how can I find the average rate over a month? I know that 48 people get struck over the year. Yeah, just divide by 12. Okay. So what was I doing there? I was taking that lambda I had for the year, dividing it by some factor. So anytime I want to go from a larger to a smaller time period, what I'll do is I'll take that average rate I was given for that larger time period, and then I'm going to divide it by some factor. I will, like, ask you this on the exam, I will not give you any example that's hard. I'm not going to give you like, I don't know, yards to feet or something like that. Even that would be easy, right? I'm going to do like year to month, day to a week, right? And I might even be obnoxious and say there's 7 days in a week or there's 12 months in a year, just so that you know what that factor is. But if you're going to want to go from a larger to a smaller time period, you need to get that average rate. You know it's going to be smaller. So how can you make it smaller? You're dividing by some factor. What if, and so once I do that, right, this would be what? 4, right? That's my new lambda. My x is 3. Now I can solve for that probability. I can also work in the other direction. So let's say the number of people that get in an accident on the Galliard was 3, right? And then I asked for the probability that, I don't know, 10 people get in an accident over the next week. Well, once again, I've changed my time interval, but now all I have to do is find this average rate over my new time interval. Well, here I'm going from a smaller to a larger time interval. So if 3 people get in an accident every day, how many people will get in accidents every week on average? 3 every day, 7 days in a week. 3 times 7 or 21. What were you doing there? Well, you were taking
that average over a day, multiplying it by that 7, or and take your average over that smaller time period and multiply it by some factor. All right, so when I'm going from a larger to a smaller time interval, divide by some factor to get my new lambda, and then it's just basically like what we were doing before. If I want to go from a smaller to a larger time interval, I'll multiply by some factor. Now I'll have my new lambda, plugging that in, it's just like what we were doing before. So there's really just one additional step, which is converting the lambda you're given into the time interval that you're interested in. Okay. Questions on that before I let you guys go? All right, so take you guys a little bit of time, but if you don't mind, on your way out, you want to write your number, write your name on the way. I'll give everybody a 10 out of 10 for the day. We'll do some exam review on Wednesday. A little bit more discussion about Poisson binomial, just to kind of start it out, but it'll be part of the review. And if you have any questions over the homework, my office hours will be Wednesday and Thursday from 2 to 4. If that time doesn't work for you, send me an email. We can set up another time.
Okay, also, you showed some example of this, and I'm struggling